Let's take a look at the relationship between vapor pressure and temperature. So if we were to take a particular substance, so in this case we'll take water, and if we were to graph the vapor pressure as a function of increasing temperature, what we would notice is that when we increase the temperature, the vapor pressure also increases, but it's not in a linear fashion. We can deal with this now, but back in the day, this posed a little bit of a problem because we didn't have the software that we needed to fit curves. So there are two scientists, Clausius and Clapeyron, that developed an equation that allowed us to, if we manipulated the values for the pressure and the temperature, we could then represent them in a linear relationship where we then could back out the information that we wanted. And so the way that this works is if we put the natural log of the vapor pressure on the y-axis, so the natural log of the vapor pressure would be our y, and then we made our x 1 over temperature instead of temperature, we find is if we were at those same temperatures and pressures, if we were to graph the natural log of the pressure against 1 over the temperature, what we would find is our data would become linearized, and then we could fit those data with the form of the equation y equals mx plus b, where y is our natural log of the vapor pressure and x is 1 over t. That then brings out the question, what is our value for m and what is our value of b? Well, b in this case we represent as c, a constant, and so that constant varies. That's a characteristic of the liquid. So with each different liquid that you look at, there will be a different value of c. But what we're really interested in is when we graph the natural log of the vapor pressure against temperature, we can pull something really interesting out of the slope. And that is the negative delta H of vaporization, or the negative delta H vap, divided by the gas constant R. All right, so if we were to make a plot of of a bunch of different vapor pressures at their respective temperatures for a particular liquid, and we were to fit that line, we could then pull or back out the delta H of vaporization. Now, that's a lot of work. And sometimes we're in a situation where we maybe have two pressure temperature pairings in a pinch and we want to back out the delta H, or maybe we know the delta H for our substance and we know the pressure or temperature at one temperature, but maybe we want to solve for the pressure or temperature at another value. And so it turns out that there is another version of the Clausius-Clapeyron equation that allows us to do just that. And the form that this equation takes is, let's say we have a substance at two different temperatures, T1 and T2. So we can take the natural log of the vapor pressure at T1 divided by the natural log, or divided by the vapor pressure at T2. So now we have the natural log of the ratios of our vapor pressures at two different temperatures instead of the natural log of one vapor pressure. This is equal to, our slope would now be delta H of vaporization over the gas constant R, and then we would put our the difference between our inverse two temperatures as our x. And so we would have 1 over T2, so we're going to put the temperature that's on the bottom and the natural log up front, minus 1 over T1. All right, and so this will allow us to solve for either the vapor pressure of the temperature or the delta H vap for two different sets of temperature conditions without having to use a data graph. Now, one of the things we practiced a lot in Chapter 10 was trying to identify which gas constant to use. And some of you in class had rightly pointed out that, with that approach, maybe the units of pressure that we're using for vapor pressure aren't going to be calling the shots on which gas constant we use. And it turns out that that was absolutely right. And so we can take a look at the units of this equation to help us figure out which value for R we're going to use. So let's say we take the natural log of our two pressures, and we have the pressure at temperature 1 in some value, but the unit is torr. We have another temperature where our pressure is given in torr. Now, this could be torr, it could be ATM, it could be bars. No matter what, we have a ratio inside of the natural log, so those units are going to cancel out to give us a unitless number. But it's the other side of the equation that's going to determine what value of R that we use. So when we're given the delta H of vaporization, that's a value for an energy change, or an energy change associated, or the heat that's released or absorbed as heat. Now, there are many different values that we can use, or many different units we can use for delta H of vaporization, but generally in this course you can count on us using joules. And so, if we report our delta H of vaporization in joules per mole, and then our temperature change is going to be 1 over Kelvin minus 1 over Kelvin, so that's going to give us units of 1 over Kelvin, we want to have a value for R that's going with units that's going to work out with the units that are on the right side of this equation. And so it turns out that we would want to use the value for R, 8.314 joules per mole Kelvin. And that reason, I'll put the temperature in Kelvin there so that's clear, so you're not going to get confused about what K means. But what this means is that our joules cancel out, our moles cancel out, and then our Kelvin cancel out. So as long as you are given a value for delta H of vaporization that is in joules per mole, you will be using 8.314 joules per mole Kelvin as your gas constant for this equation.